Okay, so continuing on from our amino acid lecture, we're going to look at the urea cycle and how ammonia is removed from the body, as well as looking at the disorders and what can go wrong. Shirt check, got Retro United, Nike, Vodafone. So yeah, looking fresh. So yeah, let's move on. So the first things first, what are the risks of ammonia? So we've got depletion of glutamate and high ammonia could drive glutamate dehydrogenase reaction to reverse. So that means the alpha ketoglutarate plus NH4 plus will make more glutamate, meaning that the ammonium ion can't be removed from the body and accumulate. And this results in more glycolysis and less ATP. So high ammonia concentration will drive glutamine synthase, get more glutamine here, which will use up even more ATP, as well as not being able to remove that ammonia from the body, and this will deplete glutamate, as glutamate causes excitosis of GABA neurotransmitters, so it's important to have a lot of glutamate in the body so these neurotransmitters can keep working. Urea cycles the metabolic pathway in which we can get rid of this ammonia, and it's turned into a less toxic product known as urea. And ammonia can cause neurological dysfunction such as seizures, coma, and death, as it can cross the blood-brain barrier. So what are the sources of ammonia? So we talked about degradation of amines, hexoamines, hydrolysis of protein, as well as we can get them from nutrition. So urea cycle, this occurs in periportal hepatocytes, so kind of the hepatocytes on the edge of the liver, and it's split into two parts. We've got phase 1 in the mitochondria and phase 2 in the cytosol. So phase 1 in the mitochondria, we get this NH4 plus and HCO3 minus, which are converted into carbonyl phosphate with the use of 2 ATP, and this is done by this carbonyl phosphate synthetase 1. So we can always use these STEM words to figure out what such enzymes do. So synthetase meaning to make, and then the name of the product usually precedes the synthetase. So we're making carbonyl phosphate, and this is upregulated by N-acetylglutamate. Then we have this carbonyl phosphate combining with ornithine. Sometimes the urea cycle is called ornithine cycle because this is recycled, which makes citrulline plus a phosphate, and this is done by OTC, ornithine transcarbamylase. And we can have a deficiency in OTC where the body doesn't have that enzyme, and when we eat meat, we can have serious side effects on the body, such as those brain damages that we talked about. So this citrulline is then transported into the cytosol by a co-transporter, which at the same time allows ornithine to enter the mitochondria as citrulline leaves. So we've got this constant inflow. So phase 2, cytosol. So then the citrulline that we just talked about combines with aspartate to make arginosuscitate, and then that's done by arginosuscitate synthetase. And then we have arginosuscitate, which breaks down into arginine plus fumarate, and this is done by arginosuscitate lyase. So again, lyase to split, so we can get that from there, and synthetase as well. This fumarate is then fed back to the Krebs cycle, where aspartate can be regenerated. Then lastly, arginine plus water, so this is where we need to drink our water, combines with ornithine to make urea, and this is done by this arginase 1 enzyme. So urea is a very water-soluble molecule, so therefore we don't really need not a lot of water is wasted when we excrete urea, and this is very important for terrestrial animals because we need to save as much water as we can in order to perform other reactions in the body. So this is kind of an overview of what happens. Kind of basically at any one of these stages, one of these enzymes can be defected and go wrong, and then we'll talk about that in a bit. So these disorders are generally inherited, and they're either issues with enzymes or a transport system. So firstly, if we talk about phenylketonuria, it says the mutation on chromosome 12 causing a defect in the phenylalanine hydroxylase, and this was where conversion of phenylalanine into tyrosine is stopped. And as we know, tyrosine is very important, and the phenylalanine is therefore accumulates in the body and in the blood, and can lead to developing brain damage because you're obviously born with this, so it affects you as you're growing up. And you can see this phenylalanine is excreted in urine. It can be easily diagnosed with a heel prick test in babies, and the treatment is basically to have a low phenylalanine diet. Then we've got this homocystinuria, so a defect in the CBS gene, which needs vitamin B6 to function. Again, excreted in urine, and this causes cystathione synthase to stop working, so therefore cysteine can't be made. But again, we can test this with a heel prick. And some of the symptoms include myopia, jaundiced eyes. So jaundice is when they go yellow and can be a sign of liver damage, clots, and osteoporosis. Then we've got this maple syrup disorder. So if we've got maple syrup, everything's sticky. It's also the recessive, and this is due to these branch chain amino acids. So leucine, isoleucine, valine, accumulation in plasma and excreted in urine. And this is quite early onset again, and that causes a defect in that BCKD enzyme that we talked about in the last video. So the blind chain amino acids can't be broken down properly. Hormones can't be made as tyrosine isn't present, as well as fumarate and acetyl-CoA. Then we've got this tyrosinemia. They can either be type 1, 2, or 3, again recessive. So type 1 is low fumarate acetoacetate hydrolase and leads to liver and kidney failure. And we can also get this Fanconi syndrome, where your proximal tubule in your kidneys, instead of reabsorbing proteins and nutrients, they spill it out in your urine. Then we've got type 2 deficiency in tyrosine aminotransferase. So we've got these skin lesions and light sensitivity. And type 3 deficiency in 4-hydroxyphenylpyruvate enzyme, and that can cause mental health problems, loss of balance, and coordination. This can be treated with low protein diet again, so low protein, low this amino acids, and a drug called nitisinone. So then we've got hyperammonemia. It's kind of a symptom of what happens when there's too much ammonia. So growth retardation, hypothermia, coordination, tremor, and seizures, and in neonates, so newborns, poor feeding and vomiting. Then we've got the citrullinemia. So this is a recessive again, and it's a type 1, and that's lack of that arginosuscitate synthase enzyme. We can also have type 2, which is mutation in citrin transporter. So as the name suggests, it's a pherine transporting the molecule. And this one, we've got high caloric diet, but also again protein restriction. And then we have arginosuccinic aciduria, again recessive, and that's lack of the arginosuscitate lyase, so the prevention of conversion to arginine. And the treatment is again high caloric, protein restriction, and supplementation. We also have N-acetylglutamate synthetase deficiency, recessive, mutation in the NAGS gene, and treatment with carbyl glutamate to make up for the deficiency. Hypoanemia, we've got type 1, so it's congenital, and defect in carbon phosphatase synthetase enzyme that we saw at the very start of the cycle, and the treatment is with arginine. So if we look here, this is again by Dr. Angela Shuren, so referencing her here. So as you can see here, we've got the cycle again, and if we just go slowly, so each one of these diseases obviously inhibits a different enzyme. So we've got citrullinemia here, then we've got arginosuccinic aciduria, and acetylglutamate synthetase deficiency here, hyperammonemia type 1 there. So yeah, you can have a overview here, and yeah, that's basically it for the urea cycle and diseases. Thank you for watching, and I'll see you in the next video. Don't forget to check the description for free trials on Amazon product, as well as the books. Yeah, follow me on social media and let me know if you enjoyed the videos. Cheers, cheerio.